So hi everyone, my name's Apoorv. As Marco mentioned, I'll be talking about our work on anomaly detection and specifically about how we can use the information that's present in pre-trained deep neural networks, specifically their curvature, to extract a measure for detecting out of distribution inputs. And so first, as a bit of motivation, so we're in this project and also beyond, a lot of places are using deep neural networks within the decision-making and control pipelines of autonomous vehicles and autonomous systems in general. And this has a lot of advantages because deep neural networks can understand high-dimensional complex inputs and turn them into things that downstream controllers can use. But it comes with their limitations because these trained models are really only as good as the data sets that they were trained on. And so specifically, if we train model in the daytime, if we change that context and suddenly now we're operating at night, then the deep neural network will still make a prediction, but this prediction could be wildly wrong and lead to unsafe behavior of the downstream system. And so it's critical that we can detect such out of distribution observations that can lead to faults in performance and impact closed loop performance. So our goal in this work is to take a pre-existing DNN that's in some sort of decision-making pipeline and equip it with a monitor that can produce an uncertainty metric that is both informative and efficient. By informative, we mean that it can separate inputs that are atypical and likely to cause the DNN to make a mistake from typical inputs where we suspect the DNN is correct. And furthermore, we want it to be efficient, which means that it will add minimal computational burden because we want these things to run in real time as part of the online kind of decision-making pipeline. And so we really need these monitors to not add a large computational burden. So as a bit of outline for this talk, I'll first start off by going into what is this notion of out of distribution and how we can use the DNN curvature to access it. Then I'll go into our contribution, which is a tool called sketching curvature for efficient OoD detection. And I'll talk about how that works. And finally, I'll go over some results. So to start, the key idea we're interested in is this notion of out of distribution. But so intuitively, this means when an input is kind of different from the training data. And one intuitive way to measure that is by distance in the input space. So for example, if we are, if these are the training data that we have, then this input here is kind of close to the training data. And so we think it's nominal, whereas this one is far away from the training data, and so it's out of distribution. While this is intuitively easy to understand, this can be hard to scale up to the complex input spaces that we want to deploy these deep neural networks on. For these input spaces are high dimensional and often highly structured. And so there's no easy metric for distance in these high dimensional structured spaces. Furthermore, this ignores the prediction task that we actually want to perform. It's not incorporating the output in any way. So instead, we propose answering this question about whether an input is out of distribution by using the information that's present in the trained DNN. So for example, in this trained the fit that we've formed on this data with this blue line. Specifically, we propose measuring OoD by asking a similar question, which is how easy is it to change our DNN's predictions without changing at a test point, without changing the predictions on training data. And so, for example, here at the nominal input, it's close to the training data. And so the training data is kind of constrained the DNN's predictions a lot at that point. But far away from the training data don't influence the DNN's predictions as much. And so, but if we can measure this degree to which the DNN's predictions are constrained by the training data, we can access a notion of out of distribution. So to really get into this question of how training data influence the DNN predictions, we take a Bayesian perspective. And specifically, we assume a probabilistic model for the DNN, where the DNN is defining a conditional distribution on the output given the input, y given x, where this is formed by a composition of a parametric distribution, for example, a Gaussian parameterized by its mean, or a categorical distribution parameterized by the class probabilities, where that parameter is actually the output of a neural network. So for example, this might be a convolutional neural network or a feed-forward neural network, and this is represented by this function f. And W here are the weights of the neural network. So in this framework, a Bayesian perspective would be to ask the question, given the data set that we have that we're trained on, what values for the network weights, W, are likely given the training data, D? And so this probability posterior distribution, P of W given data set is proportional to, by Bayes' rule, the combination of the likelihood of the data given the weights and the prior probability on the weights. And taking the log of that breaks down into the log likelihood of the data, which is the training objective for most deep neural networks, as well as the log prior plus some constant term. And it's really this constant term that makes this challenging, because we can't actually normalize this distribution tractably to actually get out an analytic form, for example, of this posterior distribution. But if we were able to characterize this posterior, this would allow us to measure this thing that we're trying to measure. Specifically, we can ask now the question, if we allow the weights to be perturbed according to this posterior distribution, how much does the output of the neural network, this probability distribution P of y given x, how much does that change from its original value at the trained value of the weights? And so in this work, we propose using this quantity as a uncertainty metric for a given input. And so this is really just measuring the intuitive notion that I talked about earlier. So as I mentioned, the kind of characterizing this posterior exactly is quite difficult. And so there's been a lot of work in Bayesian neural networks to form different ways of approximating this posterior. And one approach to doing this is called the Laplace approximation, and that's what we're going to build on in this work. So the Laplace approximation takes an arbitrary posterior, and here I'm visualizing the contours for a made-up kind of log probability distribution over the weight space. And so, for example, this might be the log posterior, and this point here might be the value of the weights that we've trained to, which we suspect will lie close to a maximum of this, this log posterior. With the Laplace approximation, what we're doing here is saying we can approximate the real posterior by a Gaussian centered around this trained value of the weights. And really what we're looking at here is a distribution that is centered around the trained weights, whose variance is related to the local second order behavior of the loss of the network. So basically it's related to a local notion of the network curvature. And so given a trained network and an ability to characterize this curvature of the network, we can approximate the posterior over the weights. Now, there's still challenges with the Laplace approximation, and most of these have to do with just scaling up to the large size of the neural network. So this Hessian that we have to deal with, defining the curvature, is an n by n matrix where n is the size of the network. And this is hard to not only compute, but also to store and invert, which you have to do to sample from this distribution, or basically create that covariance matrix. And the real challenges here come from both the second derivatives being hard to compute, and especially on large data sets, as well as just the matrix itself being quadratic in the size of the model, which for many common deep neural network models, they have millions of parameters. And so this matrix can quickly become too large to even store on most GPUs. And so there's been a lot of prior work into kind of making this more tractable. And this is focused on either imposing some sort of sparsity patterns on the Hessian, which ends up requiring regularization that can be hard to tune, or using Hessian vector products to avoid instantiating the entire Hessian, but just estimating the top eigenvectors. But this can be hard to scale to large models and datasets because computing one Hessian vector product is still a computationally intensive thing that requires looping through all the data. So now I've kind of motivated how we can get an idea of out-of distribution, a measure of out-of distribution from the DNN curvature. And now I want to talk about how our approach to doing this and solving some of these challenges with the Laplace approximation. So our approach is called sketching curvature for out-of-distribution detection, or SCOD. And the key insights in our work are to do two things. First, we use the Fisher information matrix of the neural network to approximate the Hessian. And second, we use matrix sketching tools to tractably compute a low-rank approximation of this Fisher. So the Fisher information matrix is a characterization of the second-order behavior of the output distribution of the network. And it's related to the Hessian of the network and can be thought of as a positive semi-definite approximation of the Hessian. Furthermore, it involves only first-order information of the network itself through these Jacobian terms, and uses the second-order information of the output distribution of the network, the parametric distribution we have at the output of the network. And this can be computed analytically for many common distributions. And so offline, our approach uses matrix sketching to estimate a low-rank estimate of this Fisher. And so intuitively, what we can imagine this procedure doing is looping through the training data and computing this sort of first-order information in the form of gradients in the weight space on the training inputs. And then using matrix sketching, we can extract kind of a low-rank subspace in which these gradients lie, essentially. Then at test time, we can use this Fisher information to estimate uncertainty at runtime. And so essentially what we do is we show how this uncertainty metric that I introduced earlier about looking at the local sensitivity of the output distribution to perturbations to the weights can actually be computed and estimated using the estimate of the low-rank Fisher, specifically the eigenvalues and eigenvectors, as well as information related to the gradient on a test input. And so this is can be, for the case of scalar regression, this boils down to just taking the gradient of our model on a test point and then comparing that gradient to the subspace that we computed at train time. And it's really this residual that we're measuring as a OoD signal or uncertainty metric. And so as an overview, we have this offline phase where we loop through the data set, compute this first order information, and use matrix sketching to summarize this into kind of a low-rank representation of the data set Fisher. Then at test time, we're able to use gradient information that's efficiently computable using auto differentiation, and then compare this gradient to the low-rank representation that we've learned, and use that to extract a measure of uncertainty. This measure of uncertainty is built on top of a single pre-trained neural network. There's no additional training of the network that's required. It works on any architecture. And it's efficient to compute since it's only just a few backprop operations in addition to the forward pass that you're already doing at test time. And so now, given this overview of our approach, let's jump into looking at how this works. So to test the qualitative performance of this approach, we tested it on a DNN that's been designed to as part of an aircraft taxiing system, where the inputs to this network are images from a wing-mounted camera, and the output of the network is the distance of the airplane from the center line of the runway. So we trained this model on data from the morning on a clear day, and then in this way, we're able to change the weather conditions and the time of day to simulate realistic anomalous inputs where the network may make a mistake. So I'm going to show you a video of this approach in action. So on the left, you'll see the images that are coming in from the wing-mounted camera. And on the right, I'm plotting the signal that's produced by SCOD. And I'll plot the signal over time. And if the network makes a mistake of more than 5 centimeters on its prediction, then I'm going to mark it with a black X to indicate that the network made a mistake on that prediction. Okay, so let's start the video. And so we see that first we're testing it on clear morning conditions. And so this is the same conditions on which it was trained. And we can see that in general, the network isn't making mistakes and the OoD signal is quite low. These deep neural network models can be quite brittle. So that even just as we switch to the afternoon, the network starts making significant mistakes. And intuitively, we look at this picture and we can see that there's a large shadow on the plane. So we expect that. While we as humans are able to reject that shadow and know that that's irrelevant, the neural network has not trained and learned that behavior. And so it makes mistakes. And our method is actually able to distinguish these inputs from the nominal inputs by producing a higher OoD signal. So this pattern continues as we switch to cloudy conditions. And here again, our approach SCOD is producing a high uncertainty signal. And in addition, the network is making mistakes. All of these predictions have an error of greater than 5 centimeters. And this extends again to input from a different airport where it wasn't trained on this particular runway at all. In this data set, we also had a sequence of images that were from kind of all throughout the day. So here we're looking at not specifically the morning, but maybe late morning around noon. And here we can see that these are quite similar to the training data. And indeed, our uncertainty metric that's produced here matches the training data uncertainty metric. And so it's quite low. It does go up slightly. And what's nice here is that when it goes up, the network does start making mistakes, showing that the uncertainty metric that we're producing here is actually directly related to the network's performance on this prediction task. We also tested these results quantitatively, and we compared to several baselines. So one baseline we compared to was just a naive baseline of using just the pre-trained network as an to extract an uncertainty estimate. And so for classification, you might imagine taking the softmax probabilities that a network is producing and using these to produce an uncertainty metric, for example, of entropy. But for regression, you really can't do this. So for regression, this naive baseline just produces a constant signal. Then we also compared to prior work, which performs the Laplace approximation with different types of approximations. So we compared to local ensembles, which is using the low rank Hessian, as well as this K-fact Laplace approximation that's using a Kronecker factored block diagonal approximation of the Hessian here. We also compared to deep ensembles, which aren't a pre-trained approach. It requires retraining 5 models, but this serves as kind of like almost like an oracle baseline of how well can we do if we actually retrain several models and use this commonly used uncertainty metric. So here are our results on several different domains. For more details on all of these results, I'm linking to a paper that's on arXiv, but what we see overall is across classification and regression problems, our approach is not only effective at distinguishing out of distribution data from in distribution data as measured by the area under the ROC curve. It also adds fairly little runtime on top of the forward pass of the network. So it's amenable to real-time application. So overall, SCOD is a general purpose model agnostic approach to adding an efficient and informative confidence monitor on top of a pre-trained DNN model. For more information, I encourage you to check out my preprint on this, which is on archive, linked here. And if you have any questions, I'm happy to answer them now, as well as over email, which I've posted on the slide. So thank you.
Thank you, Apurva. And I think we have time for one question. And of course, you can also ask questions in the chat, and Apurva can answer your questions in the chat. Any question for Apurva?
Yeah, I had a quick question. So when you do those computing those green arrows, right? Like you're taking the gradients from all your training data. Is this like every possible training data, or is there an optimal way to select like a handful?
Yeah, that's a great question. So let me just loop back to that slide. Yeah, so this, I guess, has it. So in our approach, so the way we do it is to loop through all the training data and compute that gradient. But obviously, storing all those gradients would be quickly a memory bottleneck. So matrix sketching allows us to get around that by incrementally building the sketch. So it's a fixed size memory sketch that we're building, and then we sketch each gradient and add it to that sketch, essentially. So we do loop through all the data, but we don't end up needing to store all those gradients. And it's just one pass through the data set. It would be interesting to see if there's ways to kind of know which data you need to look at. I think intuitively, if you had like representative samples of your data set, then it would be fine. In my own experiments, I've run it on kind of just a random subsample of my full data set, and it still works fairly well. So I think it's fairly robust to kind of how many data points you use.
Okay, cool. Thank you.